All right, so let's dive into this thing. Quantum supremacy.
Yeah.
It's been all over the place this term, but
hmm
what does it actually mean? Like,
Right.
what does it mean? What are we talking about when we're talking about quantum supremacy? And how do scientists even try to prove it?
I think one of the most captivating aspects of it is that it challenges our understanding of what a computer can do. You know, we're so used to
Right.
computers being these things that can crunch numbers,
Yeah.
but with quantum supremacy, we're stepping into a territory where quantum computers can tackle problems that would take classical computers, even our most powerful supercomputers, an impractical amount of time.
So it's like a whole new level.
It is, yeah, it's a whole new level of computing power. That's exactly right.
We've got like Google claiming they hit this back in, what is it, like 2019?
319, yeah, with their Sycamore process.
Their Sycamore processor.
Yep,
And then there was that team in China
that's right.
who did like a similar kind of thing, but with a totally different type of quantum computer.
Completely different technology. Yeah, they're Juzang and Zutongzi machines.
Right. But like, okay, how can we be sure
Yeah.
that a quantum computer is like truly doing something that a classical computer just can't?
It's a really, really hard problem to verify, and
Yeah.
that's actually one of the central challenges in the field. And one approach that they use is something called cross entropy.
Okay.
And this looks at, how well the quantum computer's output matches what we would expect from an ideal, perfectly random process.
Okay.
But even that has limitations, especially when we're dealing with the inherent randomness of quantum mechanics.
Right. Okay. So how do they actually like go about testing this? What's the setup here?
Well, with Google's research, they use these things called random quantum circuits, or RQCs,
RQCs.
and a method called cross-entropy benchmarking, or XEB.
XEB. Got it. Okay. Can you break those down? Like what are those?
Yeah, so think of RQCs as a series of, quantum operations. You could think of them kind of like logic gates in a classical computer,
Yeah.
but applied to qubits,
Okay.
which are the building blocks of quantum information.
Right.
And the random part is key. These sequences of operations are, they're generated randomly.
Okay.
And that actually leads to some really intriguing behavior.
So we're like introducing randomness right into the heart of the computation.
Yes, you are. We are. Yeah, and that randomness is part of what makes it so difficult for classical computers to simulate
Okay.
what's happening in these quantum circuits. So Google built Sycamore, their processor, with 53 superconducting qubits.
Okay.
And they're arranged in a grid. And the way these qubits interact, it creates a computational space that's vastly different from what we see in classical computing.
So I'm picturing, like, in my head, I'm picturing all these qubits kind of lined up.
Yeah.
But I'm guessing there are limitations on how they can interact, right? It's not like you can do any operation on any two qubits
That's exactly right. There are constraints.
at the same time.
Yeah.
Yeah.
And in the Sycamore processor, for example, certain operations, or, we call them gates, they can't be applied to neighboring qubits simultaneously.
Okay.
So Google's paper goes into a lot of detail about the specific layout of these gates and how they had to kind of apply them sequentially.
Yeah.
And it really highlights some of the challenges of working with superconducting qubits.
Gotcha. So we've got these randomly generated circuits.
Yeah.
They're operating within the constraints of the physical system.
Yeah.
But what makes them like behave so differently from a classical computer? What are we looking for? That's like, this is quantum.
Yeah. Well, a key part of it lies in how these random circuits create a kind of, I like to think of it as like a quantum soup
Okay.
of entangled states.
All right. Quantum soup. I like that.
Yeah. And so in a fully connected system, imagine that each qubit could interact with any other qubit directly.
Right.
Random circuits with a certain depth would lead to a very specific type of output, which is called a pseudo-random distribution.
Okay.
But Sycamore, of course, isn't fully connected.
Right.
It's that grid layout, right?
Yeah. It's got that grid layout.
Yeah. And so because of that 2D grid, the depth required to approach this pseudo-random distribution scales differently. It's proportional to the square root of the number of qubits.
Okay.
And that distinction is really important because it affects how we actually analyze the output of these circuits.
Okay. So these random circuits are like, they're churning away,
Yeah.
creating this quantum soup.
Right.
But how do we measure the randomness of that? It's not like we can just like look at it and be like, yep, that looks random.
That's right. We need a much more rigorous way to actually assess how random something is. And that's where the concept of entropy comes in. So entropy is a measure of disorder or unpredictability.
Okay.
And in this context, it helps us to quantify how random the output of the quantum circuit really is.
So higher entropy means more randomness.
That's exactly right.
Yeah.
Yeah. So there's a theoretical distribution called the Porter-Thomas distribution.
Okay.
And this describes what we would expect to see if we had a truly random quantum process.
So they compare the output of Sycamore to this ideal distribution.
Exactly. And what's really interesting is that for circuits up to a certain size, Sycamore's output in simulations actually very closely matched the Porter-Thomas distribution.
Okay.
So this meant that the quantum computer was indeed behaving in a way that was consistent with true randomness.
So they're using simulations to check for this match. But doesn't that create a bit of a paradox? Like if we can simulate it, then it's not
Yeah, that's a great
truly
problem.
beyond the capabilities of classical computers, right?
That is a great question. And it gets to the heart of why verifying quantum supremacy is so challenging.
Right. Yeah.
The key here is that while we can simulate these circuits classically, it becomes exponentially harder as the circuits get larger and more complex.
Okay.
And at a certain point, the computational resources required just become astronomical, even for the most powerful supercomputers.
So it's like they're pushing the limits of what's classically simulable
Right.
and then being like, okay, anything beyond this, that's where we start to see like the true quantum advantage.
Exactly. And remember, they're not just looking at one single metric like entropy. They're also analyzing error rates, the behavior of individual qubits,
Okay.
and even probing the fundamental physics at play to make sure that what they're seeing is really truly quantum behavior.
I'm starting to see why this is such a big deal. It's not just about like building a computer that's a little bit faster.
It's a whole different kind of computational power.
Yeah. Yeah. It's like a whole different animal,
Mm-hmm.
Okay. So back to this idea of like verifying quantum supremacy. We've talked about using cross entropy.
Right.
We've talked about comparing it to this Porter-Thomas distribution. Are there like other approaches? What about that team in China? Didn't they use a different method with their photonic quantum computer?
You're exactly right. The team at the University of Science and Technology of China used a different statistical test called the HAG ratio test to analyze the output of their photonic quantum computer.
Okay.
And it's important to remember here that there's no single definitive test for quantum supremacy. Robust verification really relies on multiple lines of evidence.
So it's like building a case,
Mm-hmm.
with different pieces of evidence
Yeah.
and all pointing towards the same conclusion.
Yeah.
Like, hey, quantum computers can outperform classical computers
Yeah.
in certain tasks.
And each approach has its own strengths and weaknesses. So, for example, the HOG test is particularly good at detecting certain types of quantum correlations that would not be present in a classical system.
So they're looking for like these statistical fingerprints that say like this could only have been produced by a quantum computer.
That's a good way to put it. Yeah. And both Google and the USTC team went to great lengths to actually validate their results. They compared them to, a variety of classical models and hypotheses to rule out any other explanations for what they were seeing. So they're very much addressing the skepticism head on, acknowledging that extraordinary claims require extraordinary evidence.
Okay, so we've spent like this whole deep dive, right?
Yep.
It's exploring how scientists are trying to demonstrate quantum supremacy, like prove it.
Yeah.
But I think the listener's probably wondering, like, so what?
Right.
Like why should we care if a quantum computer can do something a little bit faster than a classical computer?
Mm-hmm.
Especially if it's just like generating random numbers or something. Like, what's the real impact of this? What's the big takeaway?
That's a great question. And I think, while these early experiments, they might seem a little abstract, they're really laying the foundation for a whole new era of computing. Think of it like this. The Wright brothers' first flight,
Right.
that only lasted 12 seconds.
Yeah.
But it proved that powered flight was possible.
Right.
And quantum supremacy experiments are are kind of like that first flight.
Okay.
They're showing us that a whole new kind of computation is within our reach.
So it's about potential.
It is.
It absolutely is.
But can you give me like some concrete examples of what that potential could look like?
What kind of problems could these quantum computers solve that are just like impossible for our regular computers?
So imagine being able to simulate the complex behavior of molecules at the atomic level.
Okay, yeah.
So this could revolutionize drug discovery, material science. We could design new drugs with incredible precision, develop new materials with unheard of properties, even unlock the secrets of photosynthesis to create clean energy solutions.
That sounds pretty transformative.
It really does. It has the potential to be truly transformative.
Who else?
Another example, quantum computers could crack the codes that protect our online transactions and communications.
Oh, wow.
Now, this is a double-edged sword
Yeah.
because it poses a threat to our current encryption methods. But it also opens the door to developing new, more secure forms of cryptography based on quantum principles.
So it's like a race against time almost.
Yeah.
Like we need to
Yeah.
figure out quantum-resistant encryption before
That's right.
quantum computers get powerful enough to
Yeah.
break
Yeah.
the codes that we're using right now.
That's a great point. And that really highlights the importance of investing in quantum computing research now.
Yeah.
The sooner we understand the potential of this technology, the better equipped we will be to harness its benefits, but also to mitigate the risks.
It seems like there are like so many possibilities, but also a lot of unknowns, right?
Mhm.
Like where do you think the field of quantum computing is headed? What are like the big challenges that still need to be overcome?
So one of the biggest challenges is scalability.
Okay.
The quantum computers we have today, they're still relatively small, and they're prone to errors. So building larger, more stable quantum computers, this is a major engineering feat.
And those errors, those are a big deal, right? Like one little error could like cascade and kind of mess up
It can,
it
absolutely can,
the
yeah.
whole calculation.
Yeah, and so that's why error correction is another major area of research in the field. We need to develop ways to protect quantum information from noise and decoherence. It's kind of like trying to build a sandcastle on a windy beach.
Right.
You need ways to kind of stabilize the structure.
So we need to make these quantum computers bigger, more stable, and more reliable
Exactly.
before we can really like unleash their full potential.
Absolutely. But even with all of these challenges, the progress in the field is really remarkable.
Yeah.
Just a few years ago, quantum supremacy was just a theoretical concept.
Right.
And now we have multiple demonstrations of quantum computers actually outperforming classical computers, even if it's on very specific tasks.
It really feels like we're like witnessing, the birth of a new technological era.
Absolutely are. And it's an era that will be shaped not just by scientists and engineers, but by all of us.
Yeah.
As we continue to explore the potential of quantum computing, we need to have open and honest conversations about its implications for society, for ethics, for the future of humanity, really.
So as we wrap up our deep dive into quantum supremacy, what's the one thing you want the listener to remember?
I think the one thing I'd want them to remember is that quantum computing is not just about building faster computers.
Okay.
It's about opening up a whole new way of thinking about computation, about information, about the very nature of reality. It's a field that is full of wonder, full of potential, and full of challenges as well.
Yeah, it's been a fascinating journey. Thanks for guiding us through this mind-bending landscape.
It's been my pleasure.
And to our listener, stay curious, keep learning, and join us next time as we continue to explore the frontiers of science and technology on The Deep Dive.